So, good evening. You are welcome to our seventh class in Chemistry 307, Atomic Molecular Structure and Symmetry. Today, we will be looking at some highlights in the molecular orbital theory. Then we'll start a new topic on resonance. Molecular orbital, as discussed in our previous class, is a method for determining molecular structures in which electrons are not assigned to individual bonds between atoms, but are treated as moving under the influence of the nuclei in a whole molecule. The molecular orbital actually uses linear combination of atomic orbitals to form molecular orbitals, which cover the whole molecule. They are often divided into bonding orbitals, anti-bonding orbitals, and non-bonding orbitals. Some properties of the molecular orbital are the number of molecular orbitals is equal to the number of atomic orbitals included in the linear combination. Two, the number of atomic orbitals. Two, if the molecule has some symmetry, the degenerate atomic orbitals, that is, atomic orbitals with the same energy, are grouped in linear combinations, which are symmetry adapted atomic orbitals, which belong to the same representation of the symmetry of the group. Three, and the number of molecular orbitals bringing to one group representative is equal to the number of symmetry adapted atomic orbitals belonging to the representation. The HOMO and the LUMO. The HOMO is the highest occupied molecular orbital, and the LUMO is the lowest unoccupied molecular orbital. The difference in energy of the HOMO and the LUMO, termed the bond gap, can sometimes serve as a measure of the excitability of the molecule, a measure of the excitability of the molecule. And the smaller the energy, the more easily will the atom be excited. Now we'll be looking at the resonance, which is a new topic that we'll be considering today. Resonance, also called mesomerism, is a way of describing bonding in certain molecules or ions by a combination of certain contributing factors. Resonance, or sometimes called mesomerism, is a way of describing bonding in certain molecules or ions by a combination of certain contributing factors. The structures known as resonance structures or canonical structures into a resonance hybrid or a hybrid structure in the valence bond theory, so-called. It has particular value for describing the localized electrons within certain molecules or polyatomic ions where the bonding cannot be expressed by one single Lewis structures. Resonance came from analogy between the quantum mechanical treatment of hydrogen molecule and a classical system consisting of two coupled or oscillators. The coupling actually produces two nodes. The coupling produces two nodes, one of which is lower in format than either of the unoccupied vibration quantum mechanically. And this lower frequency is interpreted as a lower energy. I will take that again, that the coupling produces two notes. One of the notes which is lower in frequency than either of the unoccupied vibration quantum mechanical, which is lower in lower frequency, is interpreted as the lower energy. Instead of resonance, the localization is used nowadays. Instead of resonance, the localization is used nowadays. And resonance is a key component of the valence bond theory. Resonance is a key component of the valence bond theory used to graphically represent and mathematically model certain types of molecular structures when no single conventional Lewis structure can satisfactorily represent the observed structure or explain its properties. Resonance instead considers such molecules to be an intermediate or an average or called a hybrid between several Lewis structures that differ only in the placement of the valence electrons, that differs mostly in the placement of the valence electrons. A typical example is the benzene structure. The structure you have before you in the third slide. You see the benzene structure, how the arrangement of the double bonds. One is like a carbon copy of the other one, or it's like somebody viewing himself in a mirror, viewing yourself in a mirror. So A is a resonance of B. A is a resonance of B. If you look at the two of them, the position of the double bonds actually alters. Another example is in this diagram that we can see in the carbonate structure. You see the first one, the double bond is on top of the carbon. The second, that's the intermediate, the double bond is on what you say the right of the carbon. And the next one, the double bond, is on the left of the carbon. Or if we try to look at it in terms of the negative charges, the position of the negative charges continue to alternate. And what that means is that the double bond on the first opens up to give a negative charge on the oxygen, and the double charge on the other one, the negative charge on the other one goes to form a bond on the other side of the molecule. If we look at the next structure, that's the experimental geometry of the nitrite ion, NO2 minus, shown on the right, which is best rationalized by describing its structure as a resonance hybrid consisting of two major and equally important contributing atoms. The two atoms contributes a lot. If you look at the first one, just like in the case of the benzene structure, you will see something similar. Here in the first nitrate, the double bond is on your left. In the second nitrate, the double bond is on your right. And you see the number of hydrogen atoms and the negative ion. The negative ion are also similar to one another. They are like a mirror image of each other. And the bond angles also differ. This is what happens The equivalent side gives you actually the picture of the intermediate, what is actually happening in between the two. You see the bond angle here is 114 degrees centigrade. The next slide is almost the same slide with what we have on the fifth slide, but this one also tried to give us an illustration on how the charges are actually placed on top of one another. Now, the representation in the diagram actually means that contributing structures are typically separated by double-headed arrows. Contributing structures are separated by double-headed arrows, like something that looks like a reversible arrow, but this time it's not two half arrows, it's a single arrow pointing in both directions. The arrow should not be confused with the right and left pointing equilibrium arrow. All structures together may be enclosed in large square brackets to indicate the picture one single molecule or ion and not different species in a chemical equilibrium. So the two of them, they actually show the picture of the same thing. That means you can write it in either A form or write it either in the B format. Whichever form you choose to write it is correct and it is acceptable. It shows that they are actually pictured of one another. Alternatively, to the use of contributing structures in diagrams, a hybrid structure can be used. In a hybrid structure, pi bonds that are involved in resonance are usually pictured as curves or dashed lines, indicating that these are partial rather than normal complete pi bonds. They are partial rather than normal complete pi bonds. In benzene and other aromatic rings, the delocalized pi electrons are sometimes pictured as a solid cycle. So in other words, in such a structure, you remove the double bonds in between the alternate carbon atoms and use a cycle inside one of the ring. That tells you that there's no specific location in which actually the electrons are found. They are delocalized. In other words, it's as if they revolve around all the carbon atoms that are actually present in the molecule, that are present in the molecule. Resonance structures are employed to approximate the true electronic structure. Resonance structures are employed to approximate the true electronic structures. Though resonance is often introduced in such a diagrammatic form, in enhancing chemistry, it usually has a deeper significance in the mathematical formation of the valence bond theory. When a molecule cannot be represented by the standard tool of the valence bond theory, either by promotion or by hybridization or by orbital overlap or by sigma and pi bond formation, because no single structure predicted by the valence bond can account for all the properties of the molecule, one invokes the concept of resonance. What we have is the cyanide structure, the contributing structures to the cyanide ion that are enclosed in a square bracket. It is not commonly used because of its formal charge, but it's still a resonance structure. So in other words, sometimes the triple bond can be on the side of the sulfur, or it can go to be on the side of the nitrogen, depending on the one that is actually being employed for use. Resonance or as ordinary call to give understanding delocalization. So resonance energy or this delocalization energy is the amount of energy that is needed to convert the true delocalized structure into that of a more stable contributing structure. I take that again, that resonance energy is the amount of energy that is required to convert true delocalized structure into that of the most stable contributing structure, into that of the most stable contributing structure. The empirical resonance energy can be estimated by comparing the enthalpy change of hydrogenation of the real substance with that estimated for the contributing structure. The complete hydrogenation of benzene to cyclohexane via 1,2-cyclohexanediene and cyclohexane is exothermic. That means 1 mole of benzene delivers 208.4 kilojoule or 49.8 kilocalories is actually employed in the use. Now, when we look at the structure before us, it tells you the amount of energy that is actually used for the conversion. First is that you have 1 mole of the benzene ring. So you try to undergo titration, hydrogen is added, and the energy involved is 23.4 kilojoule to give it the next structure that you have. And furthermore, you add more hydrogen to clear again the second double bond, and you add another hydrogen again with an energy of 119.7 kilojoule to completely make it a cyclohexane molecule. So this energy that is involved in the conversion or in the changes is what we call the resonance energy. It's what we call the resonance energy. Now, there are steps that are actually involved in writing resonance. Take note of that. Steps that are involved in the writing of resonance. Steps involved in the writing of resonance. 1, the position of the nuclei must be the same in all structures. The position of the nuclei must be the same in all structures. Otherwise, they will be isomers with real existence. Otherwise, they'll be isomers with real existence. Number 2, resonance hybrids cannot be made to have lower energy than the actual molecules. I take that again, that resonance hybrids cannot be made to have lower energy than the actual molecules. Number 3, the total number of electrons and the total charge must be constant. The total number of electrons and the total charge must be constant. The total number of electrons and the total charge must be constant. Number 4, resonance hybrids must have the same number of unoccupied electrons. That is, if there are. Resonance hybrids must have the same number of unoccupied electrons if there are. Now, the resonance energy, which we actually define earlier, that resonance hybrids are always more stable than any of the canonical structures would be. The resonance hybrids are always more stable than the canonical structures. The delocalization of the electrons lowers the orbital energy ion. The delocalization of the electrons lowers the orbital energy ion, imparting their stability. The resonance in benzene gives rise into the property of aromaticity. That's why we talk about aromaticity in benzene, because of the localized electrons or the resonance structures that are found in the molecule. The gain in stability of the resonance hybrid over the more stable of the non-existent canonical structure is called resonance energy. Is called resonance energy. A canonical structure that is lower in energy makes a relatively greater contribution to the resonance hybrid or the actual picture of the molecule. Resonant energy can be used to calculate electronegativity. Resonance energy can be used to calculate electronegativity. The observation of greater delocalization in less stable molecules is quite general, and the excited state of the conjugated dienes are stabilized more by conjugated are stabilized more by conjugation than their ground states, causing them to be organic dienes. If we go back to our slides, we'll be able to look at some of these structure. We said, now let's look at the relative intermediates. Relative intermediates. A relative intermediate or an intermediate is a short-lived, high energy, highly reactive molecule. A short-lived, high energy, and highly reactive molecule. It's like what you call the excited state of an atom or a molecule that is excited. It is actually short-lived, is high in energy at that stage, and is very, very reactive at that very particular stage. Now, when generated in a chemical reaction, it will quickly convert into a more stable molecule. Normally, the intermediate states are actually transitional. They are not meant to stay in that state for a long time. That's why we call them intermediate. They are actually a formation that is expected to lead to a permanent formation. It is a state which a molecule attains, and usually at that intermediate state, it is actually not very stable at all. And it can easily either go to the product or go back to the reactant, as the case may be. So when generated in a chemical reaction, it will quickly convert into a stable molecule. Only in exceptional cases can these compounds be isolated and stored, e.g. under low temperature or matrix isolation. Under low temperature or matrix isolation. An example is reactive oxygen intermediates. Reactive oxygen intermediates, ROI. These comprise superoxide radicals. That is O2 with a minus superoxide radicals, hydrogen peroxide, H2O2, and hydroxyl radicals, OH minus, formerly originating from 1, 2, or 3 electron transfers to dioxygen, that is O2, to dioxygen, that is O2. So mostly the intermediates are also things that you can also refer to as resonance. At that state of their intermediate state, they are actually carrying some radicals, and most of the times they can be resonating to one another. The next is hydrogenation of one molecule of double bonds delivers 119 to 7 kilojoule per mole, as can be deduced from the last step. We are looking at the earlier structure that we have on the resonance energy. That is this very particular structure. That's what that explanation is actually talking about. It's trying to explain this very particular structure. And it can be deduced from the last step. The hydrogenation of cyclohexene in benzene, however, is 23.4 kilojoule, and they are needed to hydrogenate one molecule of double bonds. That is the difference between the 143.1 kilojoule is the empirical resonance energy of benzene, because 1,3-cyclohexanediene also has a small delocalization energy of 7.6 kilojoule per mole. Hence, the net resonance energy relative to the localized cyclohexatriene is a bit higher, that is around 151 kilojoule per mole or 36 kilocalorie per mole. 36 kilocalorie per mole. So far, in this class, we have been able to look at certain things. We look at the last part of the molecular orbital theory. We also try to look at how the resonance and how resonance structures are actually written. We also try to look at the resonance energy, and we also try to look at the energy involved and the examples in certain molecules that we have actually tried to examine. Once more, I thank you and I appreciate you for participating in this very particular class. I hope we meet on Thursday by 5 p.m. again, so that we'll be able to have the last lap of our class before your final examination. I also hope that you will come to that very particular class with either some questions or some gray areas which will require explanation, which will also take time to look at. Once more, thank you very much for coming, and God bless you.